Hi guys, this video covers the recursion concept and the linear recursion kind of recursive function that we will apply to singly linked lists in the next video. Let's recap the idea of recursion in general. Recursion is when a thing is defined in terms of other things of the same type. That's a very abstract definition. Let's look at a couple of concrete examples. We could say that a file folder on a computer contains files and folders. The recursive part is that a folder is a thing that might contain folders. So that's recursion happening. Certain mathematical equations have recursion. For example, the Fibonacci sequence says Fibonacci number n is Fibonacci number n minus 1 plus Fibonacci number n minus 2. So a Fibonacci number is two other Fibonacci numbers added together. That's recursive. Where this comes into data structures is that we could say that a linked list node contains one element and one node. Every node has an element, but it also has a pointer to a node. So every node is defined in terms of another node. That's recursive. What we're doing in this video is recursive functions, meaning functions you write in a programming language like C++. A function executes by executing itself. When that happens, that makes that a recursive function because part of the definition of how the function runs is to call itself and run itself again. So this is what a recursive function would look like. My void function takes an int n, and maybe some other stuff happens, but somewhere in there, at least once, the function does or could call itself, maybe on different inputs. But somewhere in there, function calls itself. There's a risk of infinite recursion, and this is similar to an infinite loop. If you make a mistake with a loop, it can run forever or until you stop it. Similarly, if you make a mistake with a recursive function, it could recurse forever. So if you just write a function that all it does is call itself, that will go on in principle forever. It will actually eventually run out of stack space, but it still is a bug that doesn't work right. So to prevent this, you need a base case. A base case is an input for which the function does not call itself. All of these recursive functions need to have an if that says, if we're in the base case, don't recurse. Otherwise, we're in the general case. We call the general case any input that's not a base case. In the general case, the function may call itself. In order to write a recursive function that works, you need to make sure it does not fall into infinite recursion. There are multiple ways of doing that, but one way is to make sure that recursive calls are always on inputs that are closer to the base case. So if you're given a general input that's far away from the base case, when you call yourself, those inputs are closer to the base case. That usually means a smaller number. If we're writing a recursive function defined on non-negative integers or something, then the closer to the base case would mean a smaller number. Or if we're writing a recursive function that operates on a data structure, a smaller input would be a smaller data structure. We peel off a piece of it. Linear recursion is a pattern for writing recursive functions. It's one way to write recursion. It's not the only way. What makes it linear is that the general case makes exactly one recursive call on a smaller input. So in linear recursion, we're not calling ourselves 2 times or 3 times or something like that. It always calls itself once on one input that's smaller. Here's pseudocode for this pattern. So a recursive function given some kind of input has a base case check. If we're in the base case, then return whatever the solution is for the base case. Otherwise, remember, return stops the function. So if we get past the if statement, that means that we're not in a base case. We make one recursive function call on a smaller input. Let's call that the sub-solution. And then we return the general solution, meaning what this whole function should return. And that should involve the sub-solution if the recursive is useful here. Designing functions like this can be tricky. There are 4 parts of a linear recursion function. If we look at the parts here, there's the base case condition that says if we're in a base case, so that condition is one part. The base case solution, what we return when we're in a base case. The arguments to the recursive call is another thing that needs to be thought through and designed. And finally, the way that you calculate the solution in the general case is also something that has to be designed. Here's a challenge. How do you design one of those parts when all the other parts depend on each other? You won't be able to get a function like this to compile or run until all 4 parts are written. So how do you write one part? You can get into this kind of spinning your wheels thing where you're like, well, I don't know what to do about the arguments to the recursive call because I don't know if the base case works. And I don't know how to write the base case condition because I don't know if the general case solution works. And you can go around and around, and you, the human designer, are kind of getting stuck in a kind of infinite recursion there. So We could call this a circular dependency. That's the term for this kind of situation in computer science. It's also sometimes called a catch-22 based on a novel that describes a similar situation. Here's one strategy for breaking out of that infinite loop or infinite recursion. It's to make kind of a leap of faith about this. So focus on just one of these parts that you feel like you can deal with and pretend that the other parts already work. So let's say we decide we're going to focus on the base case condition. When do we decide that we're in a base case? While we're doing that thinking, pretend everything else works. Pretend the base case solution works and the recursive call and the general case solution works. All I'm focusing on right now is deciding how do I know I'm in a base case. Once you get that to work, then tackle one of the other parts. Keep doing them one at a time until the whole thing works. And then kind of magically at the moment when all four are working, then the function is something that can compile and run and work. Let's look at one example, powers of 2. Powers of 2 are exponents 2 to the nth power. That's basically 2 times 2 times 2 times 2. And you have, this multiplication repeats about n times. So here's how this can work. There's a special case which we'll treat as the base case. When the exponent is 0, like 2 to the 0 power, the answer is 1. So I'm focusing just on the base case to begin with. We'll deal with the recursion later. If the exponent is 0, we return 1. That's mathematically how this works. Otherwise, we're in a general case when the exponent is greater than 1 or greater than 0. And the idea is I'm going to say, calculate everything after the first 2 times. So recursively compute all the other 2 times parts. That gives me the product of everything after the first 2 times, and then I need to multiply that number by 2. So call pow2 recursively on exponent minus 1. That gives me everything mathematically after the first multiplication sign, and then I multiply it by 2 to make the overall answer. Let's look at one more calculation example. That's the factorial number. N factorial in mathematics is written n exclamation point. It's defined as n times n minus 1 times n minus 2, and so forth until you get down to a 1. So the same kind of idea applies. I'm going to say, in the general case, calculate everything after the first n times. So calculate all that stuff with a recursive call and then multiply it by n, and that's the answer. So let's take a leap of faith in that direction down here. If I'm in a general case, I compute factorial of n minus 1 and then multiply that answer by n. Now let's get back to the base case. The base case is if n is 1, then the answer is just 1. So if n equals 1, return 1. Okay, so those are a couple examples. In the next video, we're going to see how to apply linear recursion to linked list operations.